Good day, guys. Welcome to our class for today. I hope you are doing good and you are having a nice time. Please, if you are a returning subscriber to our channel, you are welcome to this channel. And if you are just visiting our channel, you are also welcome. Please subscribe to our channel, give us a like, give us a thumbs up. Also, click on the notification bell so that whenever we upload a new lecture, YouTube will notify you. Give us a positive comment and help us to share our channel in your various social media platform. This is Normal Science Tutors Online, and this is your physics online video tutorial. You can also reach us through the WhatsApp number that's showing on your screen. Okay, so for our class for today, we'll be looking at the wave particle paradox. The wave particle paradox, that is what we're going to be looking at in our class for today. So what is the wave particle paradox? Alright, so before we go into our class, please get your writing materials ready and then be ready to enjoy the class for today. Okay, so if you are ready, I remain Oto Michael. You are welcome. So please let us go. So as I said, for our lecture for today, we are looking at the wave particle paradox. Scientists have discovered that light has two characteristics. Okay, they discovered that light and matter, they have two characteristics. So that light can behave either as a wave or as a particle. Right, so this was what actually led to the wave particle paradox. Just like, oh, light behaves like this and behave like this. So the wave particle paradox refers to the idea that matter and light have both wave and particle properties. So matter and light have these characteristics. That is, matter behave as a wave or a particle, but not as both at the same time or simultaneously. Okay, I hope you are getting. Matter can behave as a wave or as a particle, but not as both at the same time or simultaneously. So the wave nature of light explains that light can behave as an electromagnetic wave, whereas the particle nature of light explains that light consists of particles called photons. Light consists of particles called photons. Okay, that light energy can be transmitted as quanta, as quantum of energy, or as photons. Okay, so that is the wave particle, or that is the particle nature and the wave nature of light. And the wave nature of light actually can be explained by electron diffraction experiment that has been carried out. Okay, other properties that shows that light behave as a wave are refraction, interference, and polarization. So if you study your wave, you will see that wave has these characteristics. Wave can undergo refraction, a wave can undergo interference, and a wave can be polarized. The same thing also happens to light. Okay, light can undergo diffraction, it can undergo refraction, it can also undergo interference and polarization. So these properties and characteristics shows that light behaves as a wave. And one scientist that actually proved that light behaves as a wave is the scientist that is called de Broglie. So de Broglie proposed that a particle of mass m moving with a velocity v will possess a wavelength that is given by lambda over p. Now lambda over p is the same thing that lambda is equal to h over p, or lambda is equal to h over mv. The p stands for momentum of the moving particle. Okay, the p stands for momentum of the moving particle. I know that momentum is equals to mass times velocity. Alright, momentum is equals to mass times velocity. So that is why you have that lambda is equals to h over p, or lambda is equals to h over mv. Mv is momentum. Alright, now h is Planck's constants. All right, and it has a value of 6.6 and 10 power minus 64 joule per second. mv, as I've said, is a momentum of the wave particle, and then m is the mass, v is velocity of the wave particle, and lambda is the wavelength. So de Broglie was able to prove that a particle that has a mass of m and moving at a velocity v will possess a wavelength of the Planck constant all over the momentum. You know, a particle that is moving will definitely have a momentum. And momentum is equals to mass times velocity. Okay, so this was one of the scientists that actually showed that a particle or light has a wave characteristics. Okay, so de Broglie was to prove that matter and light can have wave characteristics. Another scientist that did that too was Planck's mass. So Planck's mass also proposed that radiation that are emitted, they are emitted in quanta of energy, and this quantum of energy is given by Hf. Okay, so the energy of emitted by a particle or radiated by a particle is equals to Hf, and E is equals to H times velocity over lambda. We know that velocity c is given by lambda at f, so you can actually substitute for f to have c over lambda. Okay, so this is f to give you c over lambda. So when you substitute this into this equation, you will have you will have this. Okay, so if you have this, you can actually now find your wavelength. So from this equation, E equals to Hc over lambda, you can get your lambda, which is the wavelength of the particle, to be Hc all over energy. Okay, so and that is what we have here. All right, so this is another scientist that also showed that a radioactive particle emits energy in form of quanta, and that the wavelength of the emitted radiation is equals to the Planck constant and the velocity all over the energy emitted. Okay, so we have that c is speed of light, h is Planck constant, f is frequency of radiation, and lambda is wavelength of radiation, and E is energy of radiation. Okay, so these two scientists were able to show that light or matter actually behave as a wave because they have a wavelength. Now, besides that, there are other properties that shows that light behave as a particle. So we'll look at the wave nature of light. Now we're looking at the particle nature of light. Okay. So the particle nature of light can actually be explained by emission or absorption of light, and this is more practically demonstrated by the photoelectric effects. Photoelectric effects, radiation of energy from heated bodies, and thermionic emission. Okay, so in our previous lecture, we have discussed these photoelectric effects or photoelectric emission. Okay, so photoelectric emission occurs when a photon of light hits a metallic surface, and then electrons from that metallic surfaces are ejected and they are attracted to the anode. Okay, so if the incident light has a sufficient force, it can actually remove the electron from the binding force that holds them to the metallic surface. Okay, and the electron can actually drift away and move towards the anode. So when light photon hits a metallic surface, it gives us energy to the electron on the surface. Okay, so this is light hitting this cathodic surface, if the energy of the incident photon is sufficient to force electron from the electrostatic force binding the electron to the surface, electrons are removed and extra energy moves them away from the surface. So when the incident light hits the surface and the incident light is sufficient, it will eject the electron from the surface and the electron will now be attracted to the anodes. And this can be detected by the movement of this ammeter. Alright, so this is your battery. Okay, so you see that the electron that moves out of this metallic surface, they move out as if they are particles. They move out as if they are particles. So this is one particle nature of light. Another one is a Kapton effect. This effect, when X-ray of known wavelength is allowed to collide with a stationary electron. Okay, so this is incident photon and this is stationary electron. The X-ray transfers energy and momentum to the electron. Okay, the energy lost by the X-ray is equal to the energy gained by the electron. Hence, energy and momentum are conserved. In this way, matter behaves as a particle. So this is the Kapton effect, and so the Kapton effect and this photoelectric effect help us to understand that matter has a particle nature also. Alright, so these are the basic explanation to the wave nature of light and then the particle nature of matter or of light too. Alright, so we'll also be looking at these equations in more detail. The de Broglie equation of wave nature of light and then the Planck equation of also the wave nature of light. So still on the wave particle paradox, according to de Broglie, based on what we have discussed before, the wavelength of a particle is given by lambda h over p, which is h over mv. We have said that already before that p is equals to what? Is equals to the momentum. Okay, so that is what we said before now, that p is equals to momentum. Now remember that the kinetic energy of an electron K is given by EV, which is equals to 1 electron volt, and so kinetic energy is equals to half mv squared. So if you combine this equation, if you combine this particular equation with the de Broglie equation, where you have momentum is equal to mv. Okay, so you can write this equation this way. This particular equation, you can write it this way to give you this. Now if you divide both sides of this equation by v, if you divide the both sides by v, which is velocity of the particle, you will have 2e all over v, 2ev all over v equals to mv. Now remember that mv is momentum. So if you take this one back to the de Broglie equation, this is the de Broglie equation. So substitute for mv, right? So where you have mv in the de Broglie equation, put this into where you have mv in the de Broglie equation. Okay, so if this is the de Broglie equation, the Broglie equation is equals to h all over mv. So if I'm substituting mv is equals to 2e all over v, I'll have that lambda is equals to h all over 2ev all over v. Okay, so this I can also write to be equals to hv all over 2e electron volts. So this equation, we can take it as equation 1 when we are talking about the wave particle paradox. Okay, so in case you are given an equation and you're asked to find the wavelength and you are given a Planck constant velocity and electron volt, you can easily use this equation to find the wavelength. Okay, so this one equation that is very, very important, and I want you to take note of it, and that is what I see as equation 1. Okay, I marked it as equation 1 so that you can easily take note of it. Alright, so this is equation 1, and please take note of it because we use it to solve some problems later on after now. Okay, so also if you go back to this equation, if you go back to this de Broglie equation, we have that momentum is equals to mv, and that energy of an electron is equals to half mv squared. Is that okay? It is half mv squared. So we can actually, from this equation, we can make v square this, or v, the subject of the formula. Okay, so if we make v the subject of the formula, if we make v the subject of the formula for this particular equation of kinetic energy of an electron, we have that v square is equals to 2ev all over m, while v is equals to the square root of 2. You know, when you square the both sides, you have v is equals to the square root of 2ev all over m. Okay, so you haven't gotten this, you can actually substitute into this equation of momentum. Okay, so if you put that, momentum will be equals to m, this is m, and then this is your v. Okay, so this is your m, and then this is your v. So momentum is equals to m times v, and this is your v that we have, then your m. So if you write the equation, you have p is equals to m times square root 2 electron volt all over m. Okay, so if you want to remove this square root sign that say, you have to square these other variables that are not under the square root, and that leads us to this particular part of the equation. Now from here you can actually do what? Cancel. You can cancel, right? So when you cancel, you have this, then you square the both sides to have your momentum, so that will give you square root 2 mass times electron volts. Okay, so this is, you have gotten the value of momentum here. So this is your p. So according to de Broglie, lambda is h over p. So substitute for p into the equation, so you have lambda will now be equals to this. So from this wave particle paradox, we have been able to derive two equations that are very, very key and important. This is one of them, and then this is the second one. So please take note of these two equations, as we'll definitely use them to solve some problems. That's okay. So take note of this equation 1 and then this equation 1. All we're trying to prove is the wave nature of particle, or the wave nature of light. Is that okay? So having discussed this, I think we should solve some problems. I think we should solve some problems. All right, I think we should solve some problems. Okay, so this is a sample question, and it's based on what we just discussed now. All right, so this question says that calculate the wavelength of an electron of mass 9.1 times 10 to the power minus 31 kg moving with a velocity of 2.0 times 10 to the power 6 meter per second. H is given to you. Okay, so this is actually a JAM question. Okay, it's a JAM question. Now from this particular question, you are given that mass, you are giving mass to be 9.1. This is the mass of an electron times 10 to the power minus 31 kg. You are given a velocity c. It's given to you to be 2.0. Velocity of the electron 2.0 times 10 raised to the power 6 meters per seconds, and then you know the Planck constant. Okay, so what you're asked to look for is the wavelength. Wavelength is unknown. Okay, so remember from the first equation that from the first equation that we derived, from the first equation that we derived. So from the wave equation, we had that lambda, from the Broglie equation, we had that lambda is equals to h all over p, and this is equals to h all over mv. Okay, so if you substitute into this equation, we are going to have your h, which is 6.6 times 10 raised to power minus 34 divided by m is 9.1 times 10 raised to power minus 31 times velocity, which is 2.0 times 10 raised to power 6 times 10 raised to power 6. Okay, so if you work this out, you have that the wavelength will equal to 3.64 times 10 raised to power minus 10 meters. So that you can work out from your calculator. Okay, so this is the solution to this particular problem, applying the de Broglie equation. All right, so I hope this is clear. So let's do another one. Okay, so this I actually wanted to solve it, but I just decided I should make it your test your understanding question. Okay, so the only thing I will let you know is that for you to solve this problem, you already given the voltage of the S-ray. Okay, you are given the voltage, you have the charge of the electron, you have the Planck constant, and then you have the velocity of light. So um, once you have all these variables, you know the two equations that we derived just now. Okay, so the first one is that lambda is equals to Planck constant times velocity all over 2 times electron volt. The second one that we derived just now is that h lambda is equals to h all over square root 2 m mass ev. Okay, so if you look at these two equations, you will know which one to use to solve this problem. Okay, because if you look at the two, you see that there's one variable that is not present in this question, and that is the mass of the particle. So which means this one you will not use it. This is what you will use to solve this problem. So I'll give you the hint. I actually want to solve it, but I'll give you the hint. So please just work it out and then solve it, and then you are going to have your wavelength of this particle to be 1.03 times 10 to the power minus 11 meters. Okay, so when you work it out, that's what you have. Okay guys, so thank you so much for your time. We appreciate you for being with us so far. Gradually we're already winding up our this lecture series in physics. If you go through our playlist, you find out that we have discussed physics right from the very foundation, that is from introduction to physics down to the almost last topic in physics. All right, so I think we have covered this curriculum of physics for our senior secondary school students in West Africa and generally. So we appreciate you for being with us so far. Please help us to share this channel with your friends, so that they can come and enjoy free physics class on YouTube. Okay, so we really appreciate you. But before I leave, please click on the notification bell, subscribe button if you are just visiting our channel, and then so that YouTube will notify you. Please give us positive comment, give us a like, give us a thumbs up. You know, it's not easy putting all these things together. It's not really easy. It's a lot of work, and I and my team we're always working to make sure that we bring out the best, trying to make the subject of it as simple as possible to our dear and most valued student. Okay, so we hope that we have done the little that we can. It is God that crowns people's effort. So thank you so much, and we might be rounding up this lecture series maybe in our next class. All right, so thank you for your time, and we appreciate you. Reach us through the WhatsApp number showing on your screen, and I remain your anchor to Michael. See you and have a nice day.